In this work, we introduce Arc2Avatar, a method for expressive 3D avatar generation from a single image using identity guidance. Our method generates realistic high-quality 3D heads that can be rendered from any view. Arc2Avatar exhibits strong generalization as it consistently generates realistic, faithful 3D avatars for individuals across a wide range of ages, ethnicities, and backgrounds. Given an input image of an individual, Arc2Avatar generates a realistic, identity-consistent 3D avatar on top of a 3D morphable model using 3D Gaussian splatting. The avatar can then be expressed using 3D blend shapes in an easy manner. Our method is motivated by several key factors. First, there is a scarcity of truly realistic 3D avatar generation methods that can work from just a single image. Secondly, we are seeing the emergence of human face foundation models which can work as very strong priors. Third, the strong representational ability of 3D Gaussian splats that can provide us with a strong foundation for the avatars. Fourth, the controllability provided by 3D morphable models, allowing easy control of the generated avatars. And finally, score distillation sampling, which serves as the bridge between 2D diffusion models and 3D representations. This connection allows us to integrate 3D Gaussian splats with these foundation models. However, STS has a notable well-known weakness. It often produces unrealistic results with unnatural colors and oversaturation. Addressing all of the aforementioned, we've developed an SDS-based solution that uses 3D Gaussian splats as the primary representation. This approach is built on top of a 3D morphable model template, and it's guided by a human face foundation model. The result is an expressive, identity-consistent 3D avatar generation method that is both realistic and visually compelling. In more detail, we choose Arc2Face, an ID-conditioned human face model based on stable diffusion as guidance, interval score matching, an SDS-based alternative for our optimization, and the Flame 3D morphable model as the underlying template for our avatars. An initial naive use of the default version of Arc2Face as the guidance model leads to poor results, presenting evident challenges such as Janus effects, inconsistency, oversaturation, and unnatural colors. These problems are expected though, since Arc2Face is specifically optimized to overfit on producing frontal and slightly angled facial images, which limits its suitability for generating other views compared to other guidance models. To avoid the issues mentioned, we extend Arc2Face for view augmented generation while preserving its strong prior. To achieve that, we use PanoHead to generate diverse view data rotating around the heads over 360 degrees and curate a dataset of 10K diverse high-quality identities from the initial set of generated heads to use for fine-tuning. Having the data prepared, fine-tuning must be done carefully, since PanoHead can degrade the high quality of the generated images by Arc2Face. Therefore, our solution is to use low rank adaptation with an appropriate rank and scale to achieve balance between novel view adaptability and quality. During fine-tuning, for each subject, we use the frontal sample to extract the conditioning and use the view images as targets. After fine-tuning, the model becomes suitable for guidance in an SDS-based setup. Our method employs a task-specific initialization starting by splitting the flame mesh into facial and head submeshes, densely upsampling both while respecting connectivity for the facial submesh since it is the one on which blend shapes will be applied. We then assign its template vertex a splat to establish a dense correspondence. And finally, we propose fitting facial splats to the mean facial surface, as merely assigning the RGB values of each vertex of the textured mesh to the point cloud would still result in a discontinuous representation, which is not ideal, providing thus our method with a better task-specific starting point that also enhances correspondence with the underlying template. To do that, we render only facial splats and optimize them based on renderings of the mesh with the mean texture using L1 loss. Please note that this initialization is independent of the input subject and shared among all generations and therefore can be pre-computed. We continue with the main component of our method, which is the SDS-based optimization. The process starts with the extraction of the Arc2Face ID embedding from the input image. After that, we would like to talk about the conditioning of the guidance model. Addressing Janus effects. While our LoRa fine-tuning alleviates many Janus effects, some issues persist. Our solution was incorporating view embeddings to successfully handle all remaining Janus effects without reducing identity fidelity. More specifically, we used text embeddings derived by encoding the view-dependent text with the original Stable Diffusion clip text encoder, as the Arc2Face encoder has been overfitted for identity conditioning. To maintain identity fidelity, while integrating viewpoint embeddings into the conditioning, we carefully selected a small blending factor to preserve strong identity representation while integrating viewpoint information. Moving on, to enhance alignment with the underlying 3DMM template on facial area splats, we use template regularizers, namely the L2 regularizer and the Laplacian regularizer. The outcome is improved correspondence with the template and the maintenance of structural integrity of the splats in this area. To further avoid disrupting the template correspondence, in addition to these regularizations, we use a masked 3D Gaussian splats approach by disabling densification, pruning, and opacity resets for the splats of the facial area, while enabling it for the rest of the head to allow modeling complex features such as hair without any constraints. Having clarified these important components of our method, we proceed with our SDS-based optimization, which is a two-step process. In the first step, we employ a few iterations optimizing exclusively the facial area splats, zooming in before the initialization of the optimization for all remaining splats. As evident, the mean texture fitted splats smoothly transformed to the subject's face, representing the correspondence with the underlying template. This initial optimization is important for the maintenance of the template correspondence in the next step of the process. In the second step, we simply use the remainder of the iterations to optimize the full head, starting by zooming out to the regular levels. At the end of the iterations, the method generates an ID consistent 3D avatar that can be rendered from any view, and this concludes our optimization. We split expression generation with our method into two categories, namely non-extreme expressions, where we use blend shape deformations exclusively, taking advantage of the dense correspondence with the underlying template, that ensures realistic expressions without additional adjustments, and extreme expressions, for which we propose a correction strategy where we start from the deformed splat and perform very few optimization iterations using our SDS framework, with regularizations disabled during this phase to allow flexibility. And notably, this correction strategy enhances realism in open mouth expressions by adding realistic teeth and tongue, addressing areas where splats are missing or unoptimized. Moving on with our comparisons, even though only our approach and our primary competing method, which is the recently proposed ID2-3D, are the only ID-driven methods, we also compare against some relevant text-to-3D. Regarding the results, our method achieves clearly superior realism while preserving identity, capturing fine details with natural, accurate colors, modeling challenging areas like hair with precision, and outperforming the primary competitor, which, despite their sharp geometry, lack realism and accuracy. We also conducted quantitative analysis to substantiate our claims of superiority. First, we employed the standard benchmark of identity similarity distribution, which per method reveals that our approach achieves both the highest scores and the lowest variance, demonstrating superior identity and view consistency. To further evaluate the realism of the generated avatars, we utilized the FID metric, with again our method outperforming all others, achieving the best score. Lastly, we conducted a user study involving 40 participants. Remarkably, our method collected 93% of the preferences and received positive feedback regarding its quality. Regarding expressions, we utilized a subset of the challenging comma expressions and applied a correction strategy for open mouth poses to evaluate both qualitatively and quantitatively. Our results clearly demonstrate that the generated expressions are highly realistic even for these challenging cases. Moreover, our correction strategy produces exceptionally realistic open mouth expressions. For the quantitative analysis, we assessed identity consistency by measuring the similarity between expressive renderings and their neutral counterparts. We computed the distribution for 8 evaluated celebrities, with our method once again achieving both high scores and low variance. Thank you for watching.